I'm going to kind of change where we're going and talk about productivity and why we've historically overestimated productivity dramatically. Terribly overestimated what our productivity actually is. And I'll show you why, and I'll show you some data, and I think you'll accept that premise, which means what we have to do ultimately is adjust productivity by a measure of quality. Otherwise, we really don't know what our productivity is. So let's look at how we would analyze productivity. There's a number of reasons we would want to analyze it. Number one, and the single most important reason to analyze productivity is improvement. The number one reason is improvement. People do it for other reasons, but if they're not using it for improvement, they often get off in doing the wrong thing and end up having people fake the data because it's being used for performance appraisal and other kinds of things it shouldn't be used for. Number two is benchmarking. But that requires that we have very good data and that we trust the data we're benchmarking against is just as good as the data we have, and that's rarely the case. And I'll show you why in a minute. Number three is estimation. If I have good historical data on how well we're performing and what our productivity is in different kinds of environments, then I can better estimate what it's going to take to do the next project or the next application. And finally, managing vendors. I'd like to be able to know how productive my vendors actually are and whether we're overpaying or underpaying or how they compare with their competitors. So those are the primary reasons for doing productivity analysis. There's four kinds of measures that you're going to need to do it well. The first two are obvious. This is the standard productivity measure. I have a measure of size and I have a measure of effort, and I divide one by the other and get effort per function point, or effort per line of code, or effort per something else, right? So I can use instructions, the number of computer instructions. Many people are now using function points or some version of function points, so that's a functional measure. Some people use things based off requirements like story points, which tend to not be as consistent across projects. For effort, we've got hours, but there's a lot of data we need in order to understand the hours and be able to benchmark. We need to know what roles are included and what phases are included. But there's two other kinds of things we need. We need to be able to adjust the productivity figures in order to understand what real productivity is. We need a measure of quality, which could be functional quality or structural quality or some other aspect, and we need demographics. We need things like what kind of application it is, what environment we're in, what kind of technology we're using, what kind of customer we're serving. So we need these in order to be able to understand what's our productivity under different kinds of circumstances. Because productivity can vary wildly, not based on the team so much as based on the situation that the team is working in, the technology they're using. So there's oh boy, somebody messed this up. There's several measures of size. There's some that are method-based, use case points, story points. Story points are often used in Agile. The problem is they're specific to the team, and it's very difficult to compare them or use them for any kind of analysis across teams. So they're really not a good basis for productivity analysis. They're handy for a team to understand how much it can deliver per day or how much it can deliver for a sprint within an Agile environment. There's computer instructions, lines of code. The problem historically has been that you can define lines of code in a way that gets a variation that's a factor of 10. And I've done this and done simple experiments with people and had them look at a short program and tell me the number of lines of code, and the numbers differed by a factor of 10 based on how they defined a line of code, whether they included blank lines or comments, the little squiggly that's off on a line by itself, whether they counted data, all kinds of issues. So that's been if you get a consistent way to count lines of code, you solve that problem. But then you have the problem of differences between languages, for which we can have a weighting factor. Finally, there's function points, and this was defined against the functionality delivered to the user. Many of you are familiar with function points, invented by Al Albrecht and IBM in the mid-1970s. The problem has historically been that it's really expensive. It's counted manually. A trained function point counter goes through the code and looks for all the little elements that they have to count. And so you don't do it very often. And you can't use it as a part of your software development process because it's too expensive to keep counting it day after day. And the other big problem, is that it's very inconsistent, that 2 function point counters can differ by a factor of 10, or by a factor of 10%, and sometimes as much as 20%. So it's not a consistent measure across different people doing the counts. So those are the problems historically we've had. Now, we can automate function points, and we've done that. In fact, we now have a standard for it. The Consortium for IT Software Quality, which is a subgroup or a special interest group of the Object Management Group, which is an international standards organization that standardizes UML and Corba and a number of other IT-based methods, has now developed a standard for automated function points. And so we now, and CAS has implemented it, there's some other companies that are implementing it, so we now have a way to get consistent and inexpensive counts of function points. The definition in that standard was made as close to IFPUG as possible, the International Function Point Users Group. But we had to make hard decisions about how to actually count things so we wouldn't have the inconsistency. But there is now a standard. It's not IFPUG, but it's close to IFPUG, but it's consistent and it's cheap once you get using it. So it now automates that, and that takes away some of the problems, and I suspect we'll see a dramatic growth in the use of function points as a measure of size because now we've got a way to make it cheap and consistent, and you can use it now as a part of a software development process. You can count it as often as you want to when you run your builds, and you can count the number of function points within the code in that particular build. So the weakest link has not been, and we've always thought the weakest link was size, because the argument about lines of code and function points and story points is ultimately not a technical argument. It's religious. Right? And people argue about this with the same fervor they argue about religion and politics. In fact, I feel like I'm in a parliament here. We have the conservatives over here and the liberals over here, and I guess the Swiss in the middle. But the bottom line is the weakest link is not size. There's a number of measures of size that are good. The weakest link has historically been effort. It's been the one place we have the worst data, to be honest, because too often we ask people to record, how many hours did you spend this week? And they don't do that till the end of the week or the end of the month, and they're trying to remember how many hours did I put on this project, how many hours did I put on that project, and so they're guessing, right? And especially if they're time slicing, I've got 4 different things I'm working on, and I try to remember at the end of the week how much time I spent on each, and I just guess. And so it's very inconsistent. Another problem is that it's historically underreported. I was in a major Indian outsourcer and was doing an assessment of their process, and I looked at their data and their effort data, and everyone in the building had reported 40 hours per week. And so I got the measurement person. I said, everyone is here when I come in the building at 8:30 in the morning, and everyone is still here at 9 o'clock at night when I leave, and that's 5 days a week. How do you record 40 hours? And the guy said, no, 40 hours. I said, but every day, and I added up, and it's like 40 hours, because that's all they want to show on the contract, right? They don't care. They want to just show 40 hours a week, so that's all that goes into a productivity analysis, so that's all they charge for on the contract. That data is worthless for productivity analysis. You can't use it. There's HR issues. If you ever use this kind of data in performance appraisals, people will learn how to fake it, right? They just won't record the hours. Programmers are brilliant at figuring out how to trick the system and trick the numbers. And finally, a lack of normalization. Even when you record it well, this is a problem. How many different roles were included? Did you include project management? Did you include quality assurance? Did you include the requirements analysts or your business analysts? What roles were actually included in the effort you collected? What phases were included? Did you include requirements analysis? Did you include acceptance testing? What actually was, and how many hours per person year? When I worked at ITT years ago, we had to normalize across all our different centers in different countries because they had different numbers of hours in a person year. Right? It's 2,000 in some countries, it's 1,600 in others. So we had to go back. So there's this enormous normalization that has to be done before you can actually do a good job of recording effort. The bottom line is most effort data is unreliable and it's inconsistent. It's the weakest link in all of productivity analysis. So if you want to do good productivity, you have to clean up the effort data. It has to be accurate and it has to be recorded reasonably often, and you have to have some normalized ways of who's included, what phases are included. So, and if you don't do that, you can't benchmark, which is why I worry about most benchmarking databases, because they haven't done that. And therefore, you don't really know what you're getting. All right, so the classic definition of productivity, and let's take productivity for a single release. The classic definition of productivity is that there's the volume of whatever I built, the amount of stuff we actually developed, the amount of code that I developed or modified or deleted, divided by the total effort I spent on that release. And that's classic. I mean, we get that straight out of manufacturing. The number of things we produce divided by the effort required to do it. Now, I'm going to argue that productivity in software is a monotonically declining function. Right? Everybody thinks of productivity as a baseline that's stable. Right? This is my productivity on this project, and I should be able to sustain that across projects for the next 5 years. I'm going to argue that it will decline consistently for the next 5 years unless you do something to change it. It's a monotonically declining function. Why would I say that? I mean, people will still work at the same rate, right? The problem is, let's look at some, I have an original productivity baseline across time, right? And that's what is an executive, I would think, you know, once we can establish our productivity level, we'll be able to sustain that because we have the same tools and the same processes. There's only one problem: technical debt, right? The code continues to get worse unless we do something about it. It gets harder to work with, it gets more complex unless I constantly refactor it to sustain the integrity of the architecture and to remove the stuff that just makes it more complex to work with. And as the technical debt builds up, the bottom line is it's harder to work with the code, therefore our productivity decreases over time. So unless we do something about it, productivity is a monotonically declining function across time because it's just harder to work with the code because of all the stuff we do to it, making changes and not having time to clean it up, or losing control of the architecture and just making it harder for people in maintenance to work with it. So, give you an example, and I don't have time to really go through this in depth. You'll get a copy of the slides, I hope, I assume, and you can look through the numbers yourself. But let's just assume we've got two projects, A and B. A is kind of plotters. They work really hard. They're really good. They do their work really well. And project B are the fast kids, better, faster, cheaper, really smart. We can do it really great. And so, in fact, they do. When you look at the number of function points they produce, the number of things they create, in fact, their cost, because they're able to do it faster, is $2,500 or euros per function point. It's over $3,000 or euros per function point for Project A. And therefore, we give all the bonuses and rewards to Project B, and we promote them, and we sing their praises in front of the entire company. The only problem is Project B was working so much faster that they made lots of mistakes. And they didn't have time to find them because they were faster. And this is classic in projects, whether they're waterfall or agile or anything else. Once people working too fast, staying at the office too late, they make more mistakes, and if they don't fix them, it becomes technical debt. It's something I have to fix in the future and will have to pay for during maintenance. But hey, I looked really productive in the original development. But once I get into maintenance and I look at the plotters who didn't produce many defects versus the better, faster, cheaper who produced a lot of defects, all of a sudden, if I go out and look at total cost of ownership, it was cheaper for the plotters than it was for the better, faster, cheaper. Right? So unless we can adjust for the amount of technical debt being moved into the future, being moved into maintenance, then we really don't know what our total cost of ownership is. We really don't know what our total productivity is on the application. So the bottom line is Project A is actually more productive long-term. From a corporate point of view and a long-term cost point of view, Project A is actually cheaper, even though they didn't look like that at the first release. So let's look at technical debt for a moment and kind of how would we go about measuring technical debt. I'm going to argue that technical debt is the future cost of defects remaining in the code that you know you have to fix. Right? If you don't have to fix it, it's not technical debt. You're not going to spend money on it. But if it's something you have to fix, if it's a severe security issue, a SQL injection, a buffer overflow, if it's something that would cause the code to crash, failure to do good error handling, if it's an expensive operation in a loop that operates on a large data table, these are things you know you have to fix. And so you're going to spend money on that in the future, even though you didn't spend money on it in the current development effort. So we'll look at structural problems in production code, and there's kind of two notions here. There's the principle, which is the money I'm going to have to spend to fix it. Right? The euros I'm going to have to spend to fix the problem, but until I fix it, there's interest. I mean, this works just like it would in the rest of the business. And the interest would be if I have a very inefficient piece of software, it's just going to use more resources. It's going to use more CPU, it's going to use more memory, and if I'm paying for that, if I have to add CPUs, if I'm out in the cloud environment and have to pay for more usage, okay, the bottom line is that's interest on the debt until I fix the problem. So I've got the principal, which is what it costs to fix it, and the interest, which is the fact that programmers are slower or developers are slower when they're working with more complex code. That's interest on the debt. So now, to carry further the financial metaphor, there's also business risk. And this is where we bring the CFO and the CEO into it and say the bottom line is if the system crashes and is out for 3 hours during prime retail hours, what does that cost? That's a liability. Right? That's a risk, that's a business risk and a business cost tied to it. And the fact is, the more time I'm spending fixing problems as opposed to developing new functionality, that's an opportunity cost. I'm spending my time fixing problems rather than building new code to compete with in the market, and so we just have a lost opportunity. So this is a technical debt metaphor, gives us the ability to speak with the business in terms they understand, but still capture the notion of software and what's going on in application development and in the kinds of risk and cost we're putting out in the environment when we deliver code, when we put code into production that's not of high quality. So let's look at how this works. I've got the current release, let's say release N. I do my development work. I make some mistakes, so I've got to go back and fix them during this release, and that's rework. In a low maturity environment, 40% of all the effort is rework, and that's been a fairly consistent number. It varies between 30 and 50%. But 40% is waste, right? If you're thinking lean, 40% of your work, if you're a low maturity developer, is waste. So I'll fix some of it, but there's a lot of these defects that I don't have time to fix that must be fixed. So I'm moving that out to the future. All right, that's technical debt. So we get into the next release, and I've got my original development work. I've got the rework to fix the mistakes I make with the new work I'm doing in release N+1. But I've also got the rework I move forward. And this is where we get into the productivity problem. I treat that as new work that I'll count as productive. I'll take the number of lines we had to modify or change, and I'll add that in and divide by the hours and say this is how productive No, that should never be done because that's not new work. That's rework that should have been done in release N. And if it had been done in release N, it would have counted against productivity. Right? And in fact, I'm going to keep doing this and doing this and doing this. There's things I won't have time to fix. I'll move them forward to the next release. I'll treat it as new work and give myself credit for the productivity of making those fixes. And this goes on to eternity, or until you finally retire the application. If it's COBOL, it'll be eternity because we never retire COBOL applications, at least not in banks. So I've got lots of data on that, by the way. So the bottom line is, the reason we historically underestimate productivity is rather than fixing the rework when we should have, the mistakes when we should have fixed them and would have counted against productivity, we move it forward to another release and treat it as new work and give it credit for being productive work when it's not productive at all. Had it been back in release in, it would have just been rework, right? And so our suggestion is that in release in a single release, we look at the amount of work done in that release and the effort required to do it, but we also adjust that by the technical debt we're moving forward, by the number of mistakes that we know we have to fix that we made in that release that we're not going to fix now, but we know we have to fix in the future, right? And we can measure that. We can measure that by doing structural analysis of the code and seeing what kinds of things have to be fixed. So I'm looking, and don't worry about the formula, it's a bit much to read, but the fact is I'm taking effort and I'm looking at the number of defects I get in testing that I know I'm not going to fix now, but I have to fix in the future, the number of defects I see or violations I see in structural analysis that I have to fix in the future, and I might even want to look at the amount that I've reduced the maintainability of the code by, because that just means my developers are going to be less productive. So if there's an increase in complexity based on what I did in this release, it's just going to make it harder to work with in the future. And we ought to take that and adjust productivity within this release by the number of things we know we're moving forward that we have to fix. Then we get a true measure of productivity. We can call it quality adjusted productivity. But the fact is we're really saying we're not going to hide bad code and treat it as productive work in the future. We're going to take the hit for it right now and look at how much more productive we would have been had we used methods and techniques and tools that would have helped us release higher quality code within this release, or taken the effort to fix it before it went out. So the Consortium for IT Software Quality is working on this problem. We're going to define a measure of technical debt next year, and we're going to define a measure of quality adjusted productivity. Technical debt will be based on the standards we have going through OMG right now. We have standards for automated measurement of reliability, security, performance, and maintainability. We'll take those measures and use them as a foundation for technical debt to look at how much technical debt was produced within a single release but not fixed, but move forward to future releases, and then that can become an adjustment against current productivity. And the bottom line, it would be adjusted against the hours, and therefore it would actually cause the productivity figure to be more accurate, and as a result, the productivity figure would be a better predictor of total cost of ownership and of lifetime productivity for a particular application. So that's some of the work we're doing in CISQ, some of the work that CAST is helping sponsor in CISQ, and some of the work you'll see coming out of the Object Management Group this year and next year. Thank you.